All right, so welcome back. We're starting on the third main chunk of the course. Everything that I'm going to talk about today and on Tuesday is material that will not be on the midterm next Thursday, but you'll have a few homework assignments on it, and it will show up on the final exam. I'm not putting this up here to say this is what you will do on the final exam. You won't. I'll explain what this is later. Administrative things. There's homework due on Tuesday as usual. You'll get, hopefully, your graded work back for homework 7 before the exam. The Wednesday and Thursday class meetings, because of the midterm, will be canceled, but we'll have optional review sessions. And the exam will be Thursday evening, I believe, in 1404 Siebel. We're all in one room this time. Later this afternoon, I'll post a form where you can sign up for a conflict exam if you need to. A couple of you have already sent me email. Even if you've already sent me email, please fill out the form once it shows up. Are there any other administrative, any concerns or issues or questions? Okay. So, as I mentioned at the end of class last time, what we've been talking about for most of the semester is essentially what can we compute quickly? Right. This is the sort of the core question for the algorithms component of the class, at least. So you're faced with a problem which is specified in a way that makes it clear you could, in principle, just brute force your way to a solution. But you'd like an algorithm that actually behaves somewhat reasonably quickly, right? I can always, for example, try all possible paths from S to T and pick the shortest one, but by exploiting some structure in the problem, I can actually solve this problem, much more quickly in near linear time if all the weights are non-negative. What we want to shift to now is essentially what can't we compute quickly? So I'd like, the opposite side of this coin is I'd like to develop some tools that allow me to say, you know what, given the problem that you've phrased, I can prove that there is no way to solve this problem in a reasonable amount of time, at least in the worst case. And where we're actually going to start, or we're really going to look at both of these questions simultaneously, is what can we compute? What is impossible to compute at all? Okay, there are problems which cannot be answered by any algorithm at all. There are questions for which it is impossible to write a computer program, even in principle, that will always return the correct answer. And there's a non-constructive proof of this fact, which goes something like this. The number of finite length computer programs is countably infinite. Right? I can encode any Python program, for example, as a sequence of bits, and I can think of that sequence of bits as an integer. And so I can have a one-to-one correspondence between the integers and the set of possible Python programs. On the other hand, the set of languages that I could define, sets of bit strings that I might want to recognize, is uncountably infinite. Because for every string, I have a yes/no question, and so essentially I can think of a language as an arbitrary set of integers, each encoded by one of these bit strings. And there are an uncountably infinite number of sets of integers. So I have uncountably many languages that I might want to recognize, but only countably many programs that can recognize them. In some very strict formal sense, almost every problem is unsolvable. Okay, that's a nice argument, especially if you like these kinds of countability arguments, but it doesn't actually help us identify for particular problems when is this going to be hard, when is this going to be impossible. Okay, so the two things that we're going to be looking at really for the rest of the semester, what can't be computed at all? This is a question about what's known as undecidability. The standard example of this, and I will get to a formal statement of this problem early next week, is the so-called halting problem. Here is a program written in Python. Does it ever get into an infinite loop? No matter what, is there some input that can drive it into an infinite loop? Or will it always, no matter what the input is, eventually return something? Okay? There's no way to write a computer program that will tell you that with absolute certainty. It will always be wrong on some program. Yes?
How can you say that? How can you say that?
I will prove it to you. Okay? So I'll give you the intuitive version of the proof. Let's suppose, for the sake of argument, that you have written a Python program that will correctly tell me if my Python program always halts. Awesome. Great. So here's the Python program I'm going to write. If your program says, yes, it halts, infinite loop. If your program says, no, it doesn't, halt. Now I'm going to ask you to tell me whether my Python program halts. If you return yes, then I infinite loop, and you're wrong. If you return no, then I halt, and you're wrong. That was rude, right? And the thing that makes this proof, I'll formalize this proof a little bit later, but the thing that makes undecidability work in some sense is that you can think of, I'm treating this Python program that I wrote in two different senses. On the one hand, I'm thinking of it as a program which is going to do a certain thing by calling your program. And on the other hand, I'm thinking of my program as data, which I'm going to feed to yours. And because it's possible to mix these two roles, this is the tension that brings up the impossibility of certain computational problems. Okay? It's essentially the code version of, I am lying to you. Right? I'm simultaneously talking to you and referring to the sentence that I'm speaking as the object of the sentence I'm saying to you. So the sentence is playing two different roles which are kind of interfering with each other. Yeah?
So I'm going to throw around terms that...
That's cool. So am I.
So this halting problem generally refers to like Turing.
Yes, so so Turing-Complete, again, this is something that'll be a little bit clearer later. What that means is that you have a rich enough system that you're writing your program in that you can simulate any program written in any other language or any computational device built and defined in some other model. Right? Turing machines can simulate Python programs can simulate Turing machines. So Python is Turing-Complete, and Turing machines are Python-Complete. Okay? As long as you have a Turing-Complete system, a universal computing system, you can't decide whether it will give you an answer. Yeah. Yeah, I don't know.
Like everything's always terminating?
You can possibly do that, but then the question is, here is a problem, is there an algorithm that will solve it? That becomes undecidable. Right? Here's a Turing machine. Can you write a CLO program that's equivalent to it? That is now undecidable because I don't know whether, yeah.
What if we have a function that simply
Well, that one always halts.
but we still can't do it?
No, you have to understand what I'm saying here. I want to write one program such that given any other program, it will tell whether that other program will halt. I want to write a piece of code, sell it on the Google Play Store, such that later somebody else can upload their Python code and it will say whether it halts or not. Of course, I can look at a code that says return 0 and go, yeah, it halts. It's, lots of programs can be proved to halt. But there's no systematic way, no mechanical way of proving for every program whether it halts or not. And there are specific examples where we don't know. They're very short pieces of code where we do not know whether they halt. Yeah.
If we put like one restriction on it so that you can't,
Oh, then I'll call his code and he'll call your code.
like nobody can call it.
I don't know what that means. I mean, I'm actually quite serious. I don't know what it means to say I can't call your code. Because maybe what I could do is have this guy is going to examine your code, and it's not going to call it. It's just going to build an equivalent set of aperiodic tiles that may or may not tile the plane. And that person over there is going to turn that set of tiles into equivalent input to Conway's Game of Life. And that guy over there has a Conway's Game of Life system implemented in Haskell, and then I'm going to call the Haskell code. But the logic is the same. It's just longer chains of inference. Yeah.
Is there a different set of problems or things that we can...
Yes. So there are actually two halting problems. Here's a piece of code and a piece of input. Does this code halt on this input? And the second problem is, here's a piece of code. No matter what I feed it, will it halt? Right? Both of these are undecidable. The other slightly weaker version of what can't we do is what's known as NP hardness. And here the issue is not can we do it at all. Because typically problems that fall into this class of NP hard are things like the traveling salesman problem. I have a graph with weighted edges, and I want to find a way of walking around the graph and visit every vertex exactly once, and I want to minimize the total weight of the edges I traverse. I can solve that problem by brute force and just enumerate all possible ways of visiting every vertex. Pick the best one. Unlike the shortest path problem, essentially that's the best we know how to do. So problem is NP hard, essentially if it means essentially brute force is the best you can do. That's not the formal definition, and there's a slight annoyance in that we actually don't know that any of these problems are impossible to solve quickly. All we know is that if you could solve one of them quickly, you could solve the under 128,317 of them quickly. 318, 319. Somebody proves something new, NP hard, and every 3 seconds, somebody proves something else is NP hard, and then it falls into this category where if we could solve one of them quickly, we could solve them all. And we just sort of accept as a law of nature that these problems are all hard. These are all impossible to solve quickly because the alternative is we're all stupid. Yeah.
Why is that a property that if you can solve one, you'll be able to solve?
I have to explain what it means actually formally to answer that question. But the bottom line is, for example, another NP hard problem is graph coloring. Here's a graph. Can I color the nodes with 3 colors so that for every edge, the two colors on the ends are different. If you give me an algorithm that solves the graph coloring problem in polynomial time, I can turn it into an algorithm that solves the traveling salesman problem in polynomial time. If you give me a traveling salesman algorithm that runs in polynomial time, I can turn it into a graph coloring algorithm that solves in polynomial time. Even though these two problems, yeah, they both have graphs, but the two problems are very, very different, and the reductions between them are very, very weird, right? They exist, and we'll see them, okay? Okay? Now, one problem with actually talking about this stuff formally is when we say there is no algorithm that can solve this problem, I have to narrow down what it means for something to be an algorithm in a way that I haven't had to do before. Okay? An algorithm needs to be a formal object of study so that I can say for all algorithms and have that actually mean something. And so far, we've been very hand-wavy and very fuzzy that an algorithm, oh, it's a series of mechanical steps, and it's sort of obvious that each step you can do. It's sort of obvious that you can do arithmetic. It's sort of obvious that you can do memory accesses. It's sort of obvious that you can chase pointers. But if I really want to study this problem formally, I need a formal definition for what it means to compute something. And this is a really quite nasty question. It has an extraordinarily long history. I will give you the short version. I will not geek out on you completely here. So in the 1600s, Gottfried Leibniz, who you may have heard of as one of the people who independently developed a series of notation and algorithms that we know of as the calculus. Just to make it clear, neither Leibniz nor Newton invented derivatives and integrals. The fundamental theorem of calculus that says derivatives are anti-integrals and vice versa, that was first proved by Newton's PhD advisor in his PhD thesis. So Newton didn't invent derivatives. Newton invented notation, and nobody uses his notation except physicists. We use Leibniz's notation on the rare occasions that we do calculus at all. You know, the little curly s, that's Leibniz's. The little lowercase d, that's Leibniz. Okay? But one of the other things that Leibniz did, and I think perhaps spurred on by figuring out, oh, there's this notation that lets you compute instantaneous change by only manipulating symbols, is he believed that there would be a sort of universal language for encoding any kind of question you want at all. And in particular, encoding it as a series of bits. The sort of universal binary language, essentially mapping symbols down to sequences of bits. And as he put it, where you could take any problem, be it math, science, religion, morality, ethics, and by properly encoding it into this language of symbols, you could sit down across from your opponent and say, let's calculate. Let's just run the algorithm that figures out whether, in fact, well, I don't want to come up with a moral question off the top of my head because I'm afraid I might insult somebody. Whether, let's figure out whether it's a good idea to come up with moral questions in the middle of a lecture. There. And we'll just run the algorithm. Most of Leibniz's contemporaries sort of went, yeah, that's great. I don't know what you're talking about. Then sort of the next stage is in the 1860s, 1870s, Charles Babbage built something called the difference engine. This is not in any way the first mechanical computing device, but it was one of the more sophisticated ones. And he drew up plans for something called the analytical engine, which he envisioned as a universal computing machine. So he had a small sequence of instructions that the machine could execute based on encoding the data by positions of dials inside the machine that you'd turn the crank or attach to a steam engine and it would drive the logic. So it would, for example, add these two numbers, multiply these two numbers, compare these two numbers, and do something. And he hypothesized, not exactly correctly, but close, he hypothesized that, again, any mathematical question could be answered by the analytical engine suitably encoded. He never actually built the analytical engine. He just specified it well enough that it could be programmed by Ada Lovelace. So the first programmer was not actually a programmer or even a programmer, but a programmer, theoretical computer scientist. Then there's Hilbert in the early 1900s. The same question started to come up in the mathematical world. What can we prove? Proving things and computing things are almost identical. You can think of a proof as a trace of a program. And Hilbert was, imposed a series of questions at the International Congress of Mathematics in 1910 that included, is there a decision procedure for a certain mathematical problem? And this became known as the decision problem, except, of course, it was always said in German. It was the Entscheidungsproblem. And it was one of the most celebrated open questions in mathematics. Is there a procedure by which you can prove anything? Gödel said, no, there isn't. But he wasn't particularly satisfied with the proof. And then Alonzo Church, a few years later, came up with the lambda calculus and gave a better proof. But essentially by describing proofs as a computational procedure, but again, not in a really satisfying way unless you like functional programming. If you like functional programming, then it's a beautiful way to do it. What actually sort of resolved the matter was Turing in 1936 at the ripe old age of 24. I believe he was a PhD student at the time. And at that age, he was like a third-year PhD student. 1936, he described this model of how computers work and abstracted it away into what we now call Turing machine. Now, one thing to keep in mind is when somebody in the 1930s talks about a computer, they do not mean one of these. They mean one of these. A computer is a person, okay? One who computes. And so what Turing imagined and what other people in sort of the same period were playing with the idea is, the way people do math is they have a stack of paper in front of them with symbols written on it. And according to certain rules that we memorize, based on what we hold in our heads and what we see on the paper, we can change the symbols on the paper, and then occasionally we need to put the paper aside and look at a different sheet of paper that we might have scribbled on before and we might not. And then based on the rules in our head and things we remember and things that are written on the paper, we change what's on the paper. And then maybe we go back to our earlier piece of paper and change it again, and eventually this leads us to an answer. We imagine we have an inexhaustible supply of paper, but on any particular piece of paper we can only put so much stuff. Okay? So what Turing said is, let's abstract this process. Let's imagine that instead of, a pile of paper, I'm just going to line up all the sheets of paper that I need into something you might think of as a tape. Each of those squares is one sheet of paper. Now, on any one of these cells in the tape, there are only a finite number of things that I can write into the cell. Now, for a mathematician working on a piece of paper, that finite number is incredibly large, but it is still finite. There's a limit to how small even the best mathematicians can write. So I have some sort of finite alphabet of symbols that I can write onto the tape. And at any particular time, the computer, the person, has access to only one sheet of paper. Now, in reality, of course, you can spread the paper out on your desk, but even the largest desk effectively can only hold a few hundred sheets of paper that you can see at any one time. So you might as well just think of that as that all those 100 sheets of paper are really just one cell, and you've got a larger finite alphabet, but it's still only finite. And then in a single step of computation, you can read the symbol that you're currently looking at on the piece of paper that's in front of you. You can write onto the tape, and you can move, but you can only move locally. You can only move to the next piece of paper or to the previous piece of paper. Again, in reality, I can sort of shuffle through and pick out random sheets of paper, but again, really effectively only within a small range. Right? If I've got a few million pieces of paper, I can't just stick my hand in somewhere and pull out the one I want. I have to actually look. Right? So it's abstract that by saying I'm allowed to only move one step backward and forward. And then there's some conditions that would allow me to stop and say, I'm done. I've computed the thing. Okay, and there are lots of different ways that you can define what this halting condition is. And then the last thing is that there's, the computer itself has some internal state, but only from some finite set. I have only a finite number of neurons in my head. Each of them, let's say, can be in, say at most 1,000 different states. That limits the state of my brain to being some finite set. Functionally, even the best mathematicians can't be in that many different states at one time, maybe a few thousand. But some finite number. And the nice thing about this model, even though it was really, in some sense, designed as a metaphor for human computation, it also applies to mechanical computation. That you could imagine modifying Babbage's analytical engine. The only thing that's really different about this model from Babbage's model is that you have this inexhaustible supply of memory. Babbage's machine used gears which were fixed in the machine to store various bits of data by the positions of the disks. This is a trick that goes back, to the ancient Greeks, actually. If you've ever heard of the Antikythera mechanism, there's a mechanical computational device that was found in the bottom of the Atlantic Ocean a few years ago that dates back to the 3rd century BC. People thought it was most likely a device for predicting positions of the planets and the phase of the moon for navigational purposes. But what Turing added in was this inexhaustible supply of external memory, storage. And that's about it. Now, depending on who you ask, von Neumann, who came up with the modern computer architecture, certainly was aware of Turing's work because everyone was aware of Turing's work. It was a really big honking deal. But different people disagree on whether von Neumann's development of the stored program architecture that we always use, where you have a CPU that has access to an in principle unlimited memory, but can only really access it little bits at a time, was how much that was influenced by Turing is unclear. But certainly, I don't think many mathematicians would have actually believed that von Neumann's thing would work without this, the work that Turing did. Now, about 2 weeks ago, I had the pleasure of sitting in the curriculum committee in the ECE department, where I was asked to make the case for why not just any old algorithms course, but why this algorithms course should be required for computer engineers. And the first question that was asked was, why do you need to spend so much time talking about Turing machines? No one's going to build a Turing machine. So I didn't give a very satisfactory answer then, but I think I have a better answer now that I've started actually writing up the notes and things. The reason why it's good to talk about Turing machines, it is absolutely true that this is not a machine that anyone will build for anything other than recreational purposes. You can go on the YouTube and find beautifully constructed Turing machines that use pieces of, strips of 35 millimeter film for the tape. There's a robot that actually writes a 0 or a 1 with a dry erase marker. There's a little felt wheel to erase things. There are Turing machines made out of Lego. There are Turing machines made out of Minecraft. There are Turing machines made out of all sorts of stuff. It's really fun, but it's not useful. So why do it? Part of it's historical, but part of it is I need to be able to do this. I need a model of computation that is simple enough that over a couple of lectures I can convince you that a Turing machine can take as input a description of a Turing machine and simulate it. In other words, I could just tell you, hey, you can write a Python interpreter in Python. And everybody would go, yeah. But, in this class, you're not just supposed to believe me. You're supposed to actually, follow along and make sure that I'm actually telling you the truth because I convince you. It's really hard to prove that mathematically, that you can write a Python interpreter in Python because I have to explain the semantics of Python to you, and this really isn't a programming semantics class. Whereas with the Turing machine, the semantics are clean enough and simple enough that it's possible to fairly quickly get to the kind of simulation result that we need. But it's not so simple that you have to really work painfully hard. There are other models of computation that have this property, the lambda calculus being, Church's lambda calculus being the one that comes to mind immediately. But without spending a month teaching you how to do functional programming, can't really convince you of that. Or the game of life. It's possible to simulate the game of life in the game of life. How many of you know what the game of life is? How many of you don't know what the game of life is? Okay, so the game of life is a sort of cellular automaton. You have an infinite grid of cells, which are either alive or dead, and based on some local rules, you look at whether a cell is alive or dead and how many of its neighbors are alive or dead, and that tells you in the next step whether that cell will be alive or dead. So you can simulate life inside life by building a collection of cells in life in a big 1,000 by 1,000 grid that are mostly alive if the game of life cell that you're simulating is alive, and mostly dead if the game of life cell that you're simulating is dead. But I don't want to try to go through the details of that construction. So what I really need is a simple model with a small number of instructions that nevertheless is powerful enough to simulate itself. Otherwise, I can't really talk about this fundamental question, what's impossible to compute? So I'll let you decide whether that is a good answer. But it's a better answer than tradition, because my algorithms class talked about Turing machines because the guy who wrote their textbook, no, that's not the right reason. The right reason is because it's actually useful. So let me be a little bit more formal about the definitions. Okay, a Turing machine really, I've got some finite state thing here. So if I want to define a Turing machine formally, I need to use the same kind of language that I use to define DFAs. Okay, so things are a little bit more complicated than DFAs because I've got this tape and I've got extra things that I can move back and forth. But there's still not too many components. Okay, so the first thing that I need is I need to decide what symbols I can write on the tape. This is just any finite set at all. I'm going to call it the tape alphabet. Okay, this is any finite set. Now, one of the things that I need inside the tape alphabet is a special symbol called blank. And the role that the blank symbol plays is that only a finite number of cells on this arbitrarily long tape can be anything other than blank. So if you want, you can think of the initial state of the Turing machine is every cell on the tape is blank and going off to infinity. Okay, so I just need some symbol that I can use, if you like, to represent the absence of anything else, but that I can send off to infinity. So I can more easily think as the tape as if it were infinite, rather than playing games with, when I run out of tape, just get more tape. That just makes things more confusing. And I'm also going to have a subset of the tape alphabet, which I'll call the input alphabet. So the idea is I may decide I want to answer questions about strings of bits. But when I'm answering questions about strings of bits, what that means is my input is going to be a sequence of zeros and ones written at the beginning of the tape, and the rest of the tape is going to be filled with blanks. But I want to allow my Turing machine to use other symbols besides 0 and 1. I may want to let the Turing machine use a 2, for example, or a 5, or an X, or a smiley face, or whatever, right? So I'm going to allow the working alphabet possibly to be bigger than the alphabet that I used to specify the input. Okay? Just like a DFA, a Turing machine has a set of states that it can be in. And again, this can be any finite set. And then I have 3 special states: start, accept, and reject. Start is just the state that the machine starts in. Accept and reject are 2 states that specify how the machine is going to halt. If the machine ever enters the state called accept, then immediately the machine is going to halt and turn on the green light. Yes, I like this input. If the machine ever enters into the reject state, the machine will halt and turn on the red light. No, I don't like this input. Now, the reason why I need a particular, to distinguish between accept and reject as different states is that there is a third option. You want to guess what the third option for the way a Turing machine might behave when it's given an input is? It might infinite loop. It might never answer at all. So remember, for a DFA, if you read the string and you find yourself in an accept state, you accept, otherwise you reject. Here, I really need to actively accept or actively reject, or maybe the Turing machine just can't make up its mind. Okay? And then the last thing that I need is a transition function. Now, for DFAs, the transition function took 2 arguments as input. What state am I in, and what's the next symbol that I read from the input? All right. In this case, the transition function is going to depend on what the machine's internal state is and what it can see directly in front of it. So the function takes as input a state and a symbol from the tape that it reads. And then it returns as output three things. A new state, a new symbol to write onto the tape. Now, it may be the same as the old symbol, in which case I'm not actually changing anything, but in general, I may decide, okay, I'm in state 5, and I look down and I see an A. The table tells me I should change my internal state to 7, I should erase the A and write a C, and then I should either move one step to the left or one step to the right. Okay? So, read, write, move. Okay? And this is the formal specification of what a Turing machine is. Yeah?
Is it right to save?
So this is one of the annoying things about Turing machines. There are like dozens of different ways to define them, which have minor differences. One of those minor differences is, what do I allow here? Can I go +1, -1, or can I go +1, 0, -1? And the answer is, it doesn't matter. You just have to pick one of them or the other. Okay? To keep things simple, I'm just going to say left or right. In the notes, I explain, like if you if you design a Turing machine that at some point has to stay still, it's very easy to modify it to go, oh, you wanted to stay still. Okay, move to the right, and then I'll move back. You just take 2 steps instead of 1. And you need some extra states to do that, but that's okay. You just make a larger finite set. So these minor details about what exactly the available actions are, what exactly the halting mechanism is, what exactly the means of accepting and rejecting is, what happens when you fall off the left end of the tape. You have to pick something, but it doesn't really matter what you pick. Okay? So these are the components that make up the machine. If I want to specify a machine, these are the things that I have to list. Now, some of these are easy. There's always going to be a symbol called blank, which I will always represent by a white square. There will always be states called start, accept, and reject. Sometimes I'll omit the reject and just say anything I don't explicitly write down in the transition function, just assume it goes to reject. But there'll usually be, an explicit thing called start, an explicit thing called accept, and then you just have to specify the rest of the states. And then you have to write out this giant table that says, if I'm in this state and I read this symbol, then I should write that symbol, move to this state, and move the Turing machine this way. Okay? All right, so that's syntax. That's what a Turing machine is. Now I have to explain to you a little bit more formally how a Turing machine works. So tape is, think of it as a string in the string over the tape alphabet, plus, that ends with an infinite stream of blanks. Okay? So I'm not going to distinguish, when I talk about the tape, I'm not going to distinguish between a string and the same string with some blanks after it. I'm just going to think of those two things as these are both descriptions of the same tape. The tape has, in position 0, it has a 1. In position 1, it has a 0. In position 2, it has a 1. In position 3, it has a 0. In position 4, it has a 0, and everything else is blank. Okay, so but ultimately, this is just a string over the tape alphabet. Okay? Now, a configuration, remember configuration graphs? Configuration. You can think of this as sort of the global state of the machine. The global state of the machine includes several components. It's what is the internal state of the machine? Which state in Q is the one that is active right now? What are the settings of all of the dials inside the box? but it also includes what is the content of the tape, and it also includes where is the machine currently accessing the tape. Okay, so this is a state, a string, and an integer. Q cross, cross. Okay, so I'm going to specify the state. I'm going to specify a string that tells me the content of the tape, and I'm going to specify a position on the tape. Okay, so for example, if I'm currently here in state 7 and my tape looks like this, so the first 5 symbols on the tape are 1, 0, 1, 0, 0, and the rest of the tape is blank, then my current configuration is 7, 1, 0, 1, 0, 0, 0, 1, 2, 3, 4, 5. Okay? The last number tells me my position on the tape, which means what symbol am I going to read? I'm going to read the symbol at index 5 in this string, with the understanding that if that index is off the right edge, the answer is blank. Okay? It's a little bit dangerous, to explicitly encourage out-of-bounds access to an array, but let's just imagine if you access an index that's too high, the answer is always blank. Yeah?
What's the 7 for again?
I'm in state 7.
Okay.
Right. Okay? Now, yes. So, and maybe it would be better actually if I named the states, something other than integers here. So I'm in state foo. Foo might be start. Foo might be accept. Foo might be scan or some other label that I've attached to the state. Sometimes it makes sense to actually equate the states with integers. If you remember when we were doing this, is this a multiple of 5 written in binary? In that case, it made sense for the states to be called 0, 1, 2, 3, and 4. But for other examples with DFAs, it made more sense to call the states something more mnemonic. Right? That's all that's written here. This 5 really is an integer. It represents a position. Okay. Now, the state evolves. Okay? So if my current state is P, I'm looking at tape X and I'm at position I, then the machine might decide to change to a different state. How it changes is completely determined by its transition function. Its transition function is its code, right? It says, if given that I'm in state foo and I'm staring at a blank, I look in the transition table and it tells me what state to move to, Q, what to write onto the tape in place of that blank, Y, and whether to move left or right. So whether J should be I plus 1 or I minus 1. Okay? So, this, by the way, is often pronounced yields. So, for example, if I look at my transition table and I notice that it says that if I'm state P and I'm looking at symbol A, then I should move to state Q, output symbol B, and move left. Right? Then, if I'm in a configuration that starts in state P as a string that has an A in the middle, and the length of X is equal to I, this third thing, then the configuration that I'm going to yield, this M just is the name of the machine, is Q X B Y I minus 1. Okay? So if my transition function tells me locally how I should respond to the one symbol I can see and based on what state I'm in. And from that I can infer a change in the global state of the machine. Basically just by doing simple substitution. Right? If it helps to just keep this picture in mind and not look at the notation, great. Okay. Now, given one configuration, maybe there's a sequence of these moves that gets me to another one. That I might indicate by writing a little star on top of the arrow. That means you can pronounce this eventually yields. Meaning if I start in configuration C and run the Turing machine long enough, it will eventually get to C prime. And then finally, what does it mean for a Turing machine to accept a string? Right? This is what we were doing with DFAs. For DFAs, you just chase the transition function every time you read a character, and when you run out of input, you have to halt, and you accept if you're in an accepting state, and you reject if you're not. For a Turing machine, you're allowed to go back and forth over the input, which you weren't allowed to do with DFAs. You're allowed to overwrite the input, which you weren't allowed to do with DFAs. You're allowed to write on the tape way past the end of the input, which you weren't allowed to do anything like that with DFAs. So this is the reason why I need an explicit state that says stop and say yes versus stop and say no. So I'm going to write that M accepts some string W if I start in the initial configuration where my internal state is start, what's on the tape is W, and I'm at position 0 on the tape, I eventually get to the state called accept with, I don't know, something else on the tape. That's what it means for a Turing machine to accept a string. It means if I write the string on the tape and start the Turing machine, eventually the Turing machine gets to the accept state, possibly with some other junk left on the tape. Again, some people say you have to clean up the tape. Whatever. Okay? What do you think it means when I say, M rejects W? Anyone want to guess what that actually means? Good. Okay? So, and of course there's the third option. M doesn't accept W and it doesn't reject W. It just hangs. Okay? Now, the kinds of questions that I would like to ask for a Turing machine are things like, hey, here's a binary string, tell me if it's divisible by 17. And I'd like to build a Turing machine that accepts the string if it has that property and it rejects the string if it doesn't. Right? But there's some problems where the most that I could actually possibly guarantee is if the Turing machine halts on this particular input, I will tell you that. I will accept. But if it doesn't, I might reject and I might infinite loop. Right? So there's some one-sided possibilities here that are weird. Yeah?
Accept and reject, are those just
Those are just specific states in the machine.
and every other state?
Every other state is just an internal state. Think it's a working state. I'm in the middle of something. Okay? All right. So I want to show you an example. I'm going to show you the example quickly because I think I've done more than enough walking through bags of parentheses and letters and boxes and arrows. But I at least want to give you a sense of what one of these things actually looks like. Okay? This is a description of a Turing machine And the language that this Turing machine accepts, it accepts all strings in the language and it rejects all strings not in the language, is written here. You probably can't see that, so I'll zoom in. 0 to the n, 1 to the n, 0 to the n. Okay, so all strings composed of some number of zeros followed by exactly the same number of ones followed by exactly the same number of zeros. Now, of course, this is easy to write code to recognize. If I hand you a string of zeros and ones, you could easily write a program to determine whether that string has this particular structure. The trick is doing it with this very limited set of rules. So this starts to smell a lot like programming in assembly language for a machine that has only one instruction. Okay, just pretty much exactly what you're doing. And the code that you get when you try to do this has sort of a similar looking, it's just this bag of instructions, then it's difficult to tease out any structure from it. If I just write it this way, it might be a little bit more intuitive to look at a picture that looks more like a DFA. This is a description of the Turing machine. So let me tell you what the symbols here mean. The circles with names in them are, as you might expect, states. Every one of those arrows represents a transition. All right? And the way the transitions are labeled is the symbol in front of the slash is what you would read in order to traverse that arrow. So if I'm in the start state and I read a 0, I'm going to move along this arrow to the right. If I'm in the start state and I read an X, I'm going to move down. Those are the only two possibilities. Now I'm omitting some go to the reject state transitions because it's just easier to leave them out. So I'm going to run through an example. Okay. Here is a string. Initially, I'm going to start at position 0 in state start. Okay. Now I go to start. I see a 0. What the instructions tell me is that I should replace that 0 with a $sign, and I should move to the right. I should add 1 to my index. So I'm going to replace this with a $sign, and now I'm going to move to the right. And now I'm going to be in this state called seek1. Now what seek1 does is it reads its symbol, and if it's not a 1, it leaves it alone and moves to the right. That's what that little loop on seek1 is doing. If it sees a 1, it overwrites it with a lowercase x and moves to the right and changes state. So here I see a 0, I go around the loop, I just move to the right. Here I see a 1, so I follow this transition to seek 0. I write a lowercase x here, and again, I move to the right. Now I'm in seek 0 again. I'm looking for a 0, and until I see a 0, I'm just going to keep moving to the right. So no change. Now I see a 0 again. I replace this with a little x. I move to state reset, but now I move to the left. And what reset does is it scans to the left until it sees the $sign again. Right? If I see a 0, I leave it alone. If I see a 1, I leave it alone. If I see an x, I leave it alone. But in any of those cases, I'm going to move to the left. But if I see a $sign, okay, I'll move to the left. No, I'll move to the left. No. Now here, I'm pointing at the $sign on the tape. At that point, I'm going to leave the $sign alone, go back, move one step to the right, and now I'm going to be in the start state again. Okay, you didn't see any of that because it was down below the board. Okay, so start, seek, reset. And so what happened when I did this is I replaced the first 0 with $1, the first one with an X, and the second one, the first 0 in the second chunk with an X. And I'm going to run through this loop over and over again. Every time I go through this main loop, in the first chunk of the string, I'm going to replace the first 0 with $1. In the second chunk, I'm going to replace the first 1 with an X. And in the third chunk, I'm going to replace the first 0 with an X. Okay, so after going through this one more time, I'm going to end up in the following state. I've just written this X. I'm in this state, and I'm trying to reset. Okay. Now, reset is going to just scan all the way back to the $sign. When it gets to the $sign, it moves one step to the right, goes back to start. And at this point, I notice that I'm pointing at an X. I'm pointing at something that I've already written over. The only thing that this could be is it used to be a 1. Okay? And at this point, I think I'm done, but just to be sure, I need to check that I've actually overwritten everything. And so that's what this verify loop does. It just verifies, okay, is everything to my right going to be an X? So as long as I see X's, I just keep moving to the right. Eventually, I get to a blank, and then I accept. If at any point, if I'm looking for a 0 and I don't find one because I run into a blank, or if I'm going backwards looking for a $sign and I don't find one, the transition will be undefined and I'll reject. Okay? Gives you some idea how these things actually work. All right. Now, again, I'm going to mostly, here's actually a description of, it's actually much easier to just stand in front of a whiteboard and do this, or go on to, there's a bunch of JavaScript things on the web where you can plug in the transition function and watch it go yourself. You don't want to know how long it took to type that. Okay. Let me give you a much easier one. You can see if you can figure out what this does. Okay. So this one, instead of an accept and reject state, I'm just going to have a single halt state. And here the object of the game is not to accept or reject the input string, but rather transform it into a different string. Okay, I start with some string on the tape, and when the machine halts, there will be a different string on the tape. And see if you can figure out what this machine does. So 0 here is the start state. Okay. Wanted to give you a minute or so to see if you can figure out what does this do. So talk among yourselves. That means talk out loud. Anyone have any ideas? I see people making the right hand motions. What do you think it does? Why do you think it does bitwise OR? Yeah. So notice one thing. If you're currently in a 0 state, you will always write down a 0. If you're currently in a 1 state, you will always write down a 1. The state that you move to next depends on the symbol that you read. Okay, so every step, every transition, I'm going to move 1 step to the right. If I'm in state 0, I'm going to write down a 0. But the new state is going to be determined by what was there before I wrote down the 0, which I'm going to remember, move 1 step to the right, and write it down. And then remember what's read, move 1 step to the right, and write it down. So what this Turing machine does is it takes the entire bit string and shifts it 1 step to the right, adding a 0 at the beginning, because you started in state 0. Okay? So this is one of the more useful things that Turing machines can do. You can take the input and sort of move it around on the tape. You can shift it to the left. You can, with a slightly different thing where you start at the right end of the string and read left, you can shift the string to the left. You can shift it to the right. If you use more states, which allow you to remember more symbols, you could shift it 5 steps to the right. You just need 32 states that record the last 5 things I read. Okay? So you can take the string that's written on the tape and you can move it around back and forth. Okay? With slightly more complicated instructions, you can take a string and copy it. Make a second copy of the string somewhere else on the tape. Now what that requires is that you leave a mark somehow in the string that you're copying that says, hey, this is the character I want to copy next. And you leave a mark somewhere on the tape that says, this is where I want to write the next character to. And you just bounce back and forth between those 2 marks. Every time you get to the mark on the left, you scoot it to the right and read something. Every time you get to the mark on the right, you scoot it to the right and write something. Okay? You can do simple arithmetic. If I give you a string of n ones followed by a 0 and then a string of m ones, how would you compute a string of n plus m ones? Take the 0, write a 1 over it, go to the end, erase the 1. Okay? So I can do addition. I can also do subtraction by sort of canceling out ones until one of the strings goes away. By stacking addition on top of itself, right, I can build counters, so I could add something to itself many, many times. I could implement multiplication. By implementing multiplication many, many, many times, I can implement powers. Okay? Now, at the beginning of class, I showed you this monster. Okay? Again, I'm not going to walk through this step by step. I'm going to explain this in a little bit more detail again in the notes. What this machine does is it takes the input consists of 2 bit strings with a plus symbol in between them. And these 2 bit strings represent binary numbers. And what this machine does is it replaces string w plus string x with the binary representation of w plus x. Okay? So they're bits of the machine that, like, okay, I need to make some room by doing that shifting thing, and then in the main loop I have marks on the bits that I want to read and write, so I'm going to go over to x, I'm going to read a bit, then I'm going to go back over to w, and I'm going to add it to the appropriate bit, except I have to remember carries, which I'm going to remember in my internal state. So add 2, for example, means I want to add 1, but I had a carry bit in the previous iteration. Add 0 means I want to add 0, and I did not have a carry bit in the previous iteration. Add 1 is I want to add 0, but I had a carry, or I want to add 1 and I didn't. And then based on what I get when I get to a symbol that's marked the one I want to add to, if I'm adding 0, I'm definitely not going to get a carry. If I'm adding 2, I definitely am. And if I'm adding 1, it depends on whether I'm adding it to a 0 or 1, whether I get a carry or not. And then the rest of this is just bookkeeping, to go back, zoom the head back and forth between the two parts of the numbers that I'm adding up. Okay? As I said, this starts, when you start looking at these things, actually designing them, it's useful to spend a little bit of time building these things just to get a feel for how they work. And we're going to spend some time tomorrow in the lab actually doing it. But really what I'm trying to build up is a sense of confidence that when we start talking about things in a higher order language, when I say, oh, and then I have the Turing machine shift everything to the left by 8 steps, you go, oh, sure. Right? This now becomes a primitive operation which won't be implemented in constant time. I don't really care about time in this model, at least not yet. But it's just something you know you can do. Okay? Now, on Tuesday, I'm going to try to develop a somewhat more sophisticated vocabulary of things that one can do with these Turing machines, building up from this basic level of I can shift things around, I can make copies of things. If I have a string here, I can look for the other copy of that string somewhere on the tape. Just that by itself is enough to allow me to build what's called a universal Turing machine. So a universal Turing machine is the Turing equivalent of a Python interpreter written in Python. A universal Turing machine takes as its input a description of a Turing machine and its input. And then what the universal Turing machine does is it runs that code on that input. Just the way that, a Python interpreter written in Python, or really a Python interpreter written in JavaScript might be a better metaphor. The JavaScript program is the machine that's actually running, but the way it's doing, what it's doing when it runs is it's simulating a Python program, which is in turn absorbing some input. Okay. And then once I have this universal Turing machine, a Turing machine that can simulate any other Turing machine as long as you give it the right set of instructions, just like you would give software to a real computer. Now we have the groundwork that allows us to prove that, for example, you can't prove that things halt. Because if you could, you would just feed the source code of that halting Turing machine into itself with a knot on it, and the universe would explode. Okay? I'm happy to answer questions, but if not, see you next week.